Well, what do we know about a matrix? Any of these state equations that describes what? Well, I get characteristic equation. In fact, I can define the characteristic equation for this. Right? I can find the s I minus our A control and get the characteristic equation. And what order it is, you know, S to the n plus your term. Yeah? And the case being involved in that. So I know I can get a characteristic equation. What characteristic equation do I want? It's up to you. I can make any characteristic equation I want. So here's where design comes in. The roots are designed. I specify what roots I want. I can specify a desired characteristic equation, solve for k for every one of these things, and solve, and then I have my values of k. So what you're doing is you're going to find what roots do I want. In transfer function classical controls, the roots were called what? The poles. First of all, where do I want those poles? Let that play. I want to be negative real parts. Right? That's one criteria. Right? Guarantee stability. Other criteria where I want to know? Well, what type of damping do I want? What sort of natural frequencies do I want? So forth. And note I can specify every single one of them. Big advantage of this over classical controls. I specify every single term of my characteristic equation. So that's fundamentally what we're doing. It's called pole placement. I want my closed loop poles to be here. Figure out what gains make them there. All right. Now some of these forms, this is very nice. Let's look at our simple form right here. This one's going to be quite trivial to do. Right, here's an A being good. So here's the short form. Right? And I said, well, use is equal to A equals x. We put that in, so I have this form. A plus A B print K. X. And K is what? Well, it's a vector of the row vector. What's B times K? I'm sorry. Every column. So, does have to be a row vector. Transformation we have here. What's B times K? Yeah.
So where's the input to the system here?
Right now there isn't any. It's just the feedback.
Okay.
All right. Then we'll do how to do inputs later. Right now we're just looking at closed loop A matrix.
Okay.
Right? You'll see why some forms are nicer than others. So for this one, what's B times K?
K2.
It's 0, 0, K1, K2. Right? Linear algebra. So what's A plus BK? Here's my matrix. Plus 0, 0, K1, K2 equal what? 0, 1, K1 minus 2, K2 minus 3. Right? What's the characteristic equation for that? What goes there? K2 minus 3. What goes here?
Should it be 3 minus K2? 2 minus K1?
Oh, yes, 3 minus negative. Yeah. Now let's say we have some desired characteristic equation. How do I get K1 and K2? These I specify from what I want my system to be. I can very easily solve what K1, K2 are. I can just drop right on out. So this controllable form, finding the feedback thing, is very simple. Right? Very, very simple. That's why we want it in this controllable form. What would it be if it were in a different form? Okay, something like that. Well, B times K is still what? So that, a little bit messier this time. So this is what? K1, K2, 2K1, 2K2. So I have to add these up. A plus BK. In this case, I have minus 1, 2, 3 minus 2, plus K1, K2, 2K1, 2K2. And this is a little bit messier. K1 minus 1, K2 plus 2, 2K1 plus 3, and 2K2 minus 2. And I want to find the characteristic equation for that. S K1 minus 1 minus K2 minus 2 minus 2K1 minus 3 S times 2K2 minus 2, and finally determinant of that. Now what do I have? Not quite as clean. Still 2 equations, 2 unknowns, not too hard to solve. But I had 4 or 5 states. Now I have 5 simultaneous equations to solve, and it gets to be a little bit more awkward. Right? But what if I could transform my A matrix into controllable form, really easy to solve for the gains, and then transform them back? Right? And that's what we'll do. That's why we want to transform from one form to another. Okay? some forms, very simple to get the controller gains. Controllable forms, trivial to get it. Other forms, not so trivial, especially for a higher order system. Okay? That makes sense why we're doing all this in your algebra, all these transformations. Yeah.
What's the observable form of it?
The question is, what's an observer? Well, we're assuming one thing here. That I have gains on every single state. What if I can't really put a transducer in every state? Or I don't want to, it's awkward. Right? What do?
You have to extrapolate this state?
Yeah, that's called an observer. I'm going to make something that estimates what that state is. Right? Another reason I might want that, an observer, is they are what's called filters. So if I have a noisy system, I can use an observer to kind of take care of noise in that transducer. Right? That's called an observer. And then I have them both together as a control observer. And guess what's the easiest way to find gains for an observer? Observable form. Right? So that's why we want to be able to take some system, put it in control form, solve for the control gains, piece of cake. If I put it in observer forms, we'll see that we can solve for the observer gains, have similar structure to this very easily. Okay. That's kind of this whole class in a nutshell, right there. The rest of it's just solving equations. There's a whole other form. Here we set a desired set of roots. We set a desired characteristic equation, which is perfectly fine. But what if I says, I don't want to set desired poles, but I want to minimize fuel consumption. I want to minimize time. Whole other realm here. Right. Which I'm not going to define this, but I'll define what my states want to be. So I'm going to define, I want my state to be something or other. Not with the roots there. That's what we get into what's called linear quadratic regulators. And you can do that with observers. You know, I have noisy things. And I'm going to make this, I'm going to minimize noise on what we do. That's called a Kalman filter. Ever heard the term Kalman filter? We'll go through this briefly in this class. Yeah, it's essentially an optimal filter. Okay. All right. What else do we need to know about these systems? What's the default thing you should always check for?
Stability.
Okay? Stability. Okay? How do we determine stability for a system? Okay, the state form is really almost trivial. All I have to do is check the what. How do I check for stability? Yeah.
You look at the coefficients of the signs?
What coefficient, what signs?
Of the, you're talking about the state equation, right? Or the
I want to check the state form.
characteristic equation?
Okay, what characteristic equation, or even easier, really, a characteristic equation, what am I solving, looking for in characteristic equation? So for a stable system, I want all my roots to be at that point, negative real parts. How do I get roots for a state system? What are the roots? In fact, roots of what?
Take the eigenvalues.
Roots of that, yeah, eigenvalues. I simply know eigenvalues are negative real parts. And you're done. So, how to sum that? Now, the advantage of a state system over the transfer function approach is when I do my feedback controller, do we need to really check for stability? Why should that be a big deal? Why might it be a big deal for transfer functions? Because how many choices am I making for my character equation for a transfer function controller? Typically 2 out of 3 or 4. In state form, how many routes am I designing for? All of them. So I can say they're all stable, and I know they're all stable. I don't need to worry about the ones I'm not trying to control, because I'm controlling all of them. It's, the whole thing on stability and state system is a lot simpler. Make sense to this? Okay, so you understand why we're doing all these transformations? We're going to spend a lot of time on getting these going. Other questions you have? Let's get, yes.
If the controllability matrix isn't full range, is that implied?
We're going to get into what controllability and observability is. That can be a real problem. Because we've assumed what in our system here?
We're skipping.
We can measure all the states. I can see them all. And I can control them all. The question is that possible? That's what controllability and observability is.
My head hurts. That was wonderful. Good, like the